Question 1. The following compound with the formula C4H8O2 is an ester. Give its structure and assign the chemical shift value. So the first thing I would do with this problem is I'd take a look at the molecular formula and say, okay, well there's 8 protons in the compound, so H8. What is my HDI? So HDI for this compound, you plug the numbers in the formula or you just remember it. Anyhow, the HDI is 1, so there's only one double bond in here, and since we know it's an ester, we have this part, okay, or this moiety, or this functional group, okay, the ester, and we must have a couple of R groups coming off of that. So let's just remove the R groups for now. We'll take those off. There we go, and we'll take a look at our spectrum, because we know we have an ester, and we've already taken care of the HDI. The next thing I would notice is that the integrals or the integration are given for us in this problem. So it says 2 here, 3 here, and 3 here. And we don't have to do a whole lot of number wizardry, so to speak. We can see that we have 2 protons here, 3 protons here, and 3 protons here. How did I know that? Because if I add 2 plus 3, I get the number 8. So I don't have to do anything special with the integration. I can see that this quartet here, so this is called a quartet, the 4 peaks, that must represent 2 protons. This singlet here around 2.1, that must represent 3 protons. And this triplet down here, upfield, that must represent 3 protons. So there we go. We figured out the HDI, and we know that we have 2 protons, 3 protons, and 3 protons represented by these 3 different signals. Another thing I would notice right away is that you see you have a quartet and a triplet, and in 3101 and 3102, when you have a quartet and a triplet, and you can see that the distance between the peaks, we call that the coupling constant, so that those distances there, I'll just remove them. And the distances here, when you can see that those look equal, those are called the coupling constants. And that would tell you right away that these 2 signals, so the quartet and the triplet, that must represent an ethyl group. So I'll put CH2, CH3 there. And how do I know that? Well, if I write down, if I had just some kind of generic structure, if I have CH2 and CH3, the n+1 rule says that the number of protons that are adjacent to the protons in question, you add 1 to that number, and it tells you the number of peaks that you will see in your signal. So what does that mean exactly? Well, if I look at my methylene, I can see that that's coupled next to 3 protons. So if I say 3 plus 1, so that's the n+1 rule, 3 plus 1 is going to give me 4. So that means that those 2 protons in this methylene, that should give me a quartet. Okay, and then if I look at the CH3, those are coupled next to 2 protons. So if I say, okay, well, 2 plus 1 is 3, so that means the CH3 should give me a triplet. So that tells us that this is our CH3 in our ethyl group, and this is our CH2 in our ethyl group. If we have 3 protons that are represented by a singlet, that means they're not coupled next to any protons whatsoever. So therefore, this must be a CH3 that is just by itself. So we have the ethyl group, the triplet, and the quartet, and we have the methyl by itself. So what could I do? Well, I could just start, kind of messing around with it and say, well, there's only 2 possibilities for the structure. I could either have this as a structure, so where I have my CH2, CH3 like this with my CH3 over here. So that's one possibility. And the other possibility, let's just draw it down here quickly, would be, I'm going to run out of space here. Anyhow, would be this CH3, CH2, and then O, and then CH3 like that. Okay, so those are my 2 possibilities. Now, the correct answer is this one here. So that's the one I wrote out a little bit bigger, and we'll see why. So the first thing I would do, or the next thing I would do, is I would look at each one of these structures and I'd say, okay, well, can I estimate what my chemical shifts would be? And the table that you'd want to use to do that is found in Klein's book, and it's table 15.1. So if I look at this methyl group here, okay, that methyl group, a methyl group usually comes out at around 0.9 parts per million, but according to the table 15.1, I should add 3 to that, because that's an oxygen of an ester. So that would give me a signal around 3.9 ppm. And you can see that my singlet is around 2 ppm. So immediately you can see that there's something seriously wrong with this structure. It's not sounding good. But if I go over here to the structure that I have on the top left, I take this methyl group and I say, okay, again, a methyl comes out at around 0.9, but this time the methyl group is next to a carbonyl. And when it's next to a carbonyl, I add 1 part per million, so that would give me 1.9 parts per million. That's much closer to what I'm seeing here, which is around, looks to me like around maybe 2.05 parts per million. So that's a much closer approximation, and that looks a lot better to me. Over here for this methylene, a methylene usually comes out around 1.2 parts per million, but we have to add 3 to that because it's next to an oxygen of an ester. So we're going to add 3 to that. So that would give us 4.2 parts per million, which seems reasonable because this peak here, the quartet, comes out around, I don't know, maybe around 4.15 parts per million. But that looks pretty good to me. And then lastly, my methyl group here, you can see it's around 1.12, maybe around, I'll just write it over here, maybe around 1.25 parts per million, something like that. Anyhow, so we know that a methyl group comes out at around 0.9 parts per million. I'm going to add 1/5 of 3 because of the oxygen of the ester. So 1/5 of 3 is 0.6. So I get around 1.5 parts per million. And that's a lot closer to my 1.25 parts per million. So there we go. Now we've determined the correct structure of the compound, but we're still not done. The last thing it says is assign the chemical shift value. So the proper way to annotate a spectrum is that you start at 0 parts per million, and you go from upfield to downfield, and as you progress along the spectrum, going from right to left, you label each peak with a letter of the alphabet, starting with A, and then B here, and then C for our quartet. And then you write the appropriate letter next to the protons which it represents. So I have my methyl group, which is represented by the triplet. So that must be this methyl group here because it's adjacent to the CH2. So I put A here. I put B for this methyl because it's not coupled next to any protons. And then C for this methylene. I'm going to put that here because it's split by the 3 protons on the methyl group. And again, 3 plus 1 gives you 4. So there you go. That's the strategy to solve problem number 1.